Hello, everyone. Thank you for joining us this afternoon. My name is Braden Mulhook. I'm the director of the Center for Theology and the Natural Sciences here at the Graduate Theological Union. And thank you very much for being here for our public forum today. Today we're going to be celebrating one of our graduating doctoral students, the Reverend Dr. Hyung-Joo Lee. And Bob Russell is going to give us some introductory comments to sort of situate Hyung-Joo's dissertation topic, which will then help facilitate the presentation. Afterward, the Reverend Dr. Lee will give his presentation, and there'll be time for questions afterward. So first speaking will be uh, Dr. Robert John Russell, who is the founder and original director of the Center for Theology and the Natural Sciences and Professor Emeritus of Theology and Science here at the Graduate Theological Union. He's also the founding co-editor of our journal, Theology and Science. And following him will be the Reverend Dr. Hyung-Joo Lee, who is about to graduate on next Thursday from the GTU with his PhD, with his dissertation entitled Our Inflationary Big Bang Universe is Creation as the Ground for Redemption and is characterized by introphysics emergence, under the supervision of Robert John Russell, Ted Peters, and Phil Clayton. He also holds a PhD in physics from the Korea Advanced Institute of Science and Technology for his research on a cosmological model based on supersymmetric quantum field theory. He is currently working as the editorial research assistant here at CTNS. Okay, Bob, take it away.
Okay, thank you. So I'm going to just give a brief introduction to eschatology and cosmology before Hyung-Joo Lee's work, to give you a sense of the background out of which he's coming and bringing us new ideas. So in the 70s and 80s, gravity was separated out from particle physics, and gravity through Einstein's general relativity predicted the Big Bang cosmology, including T equals 0, the beginning or Big Bang, and the far future as freeze or fry. And it was deterministic. And look at the difference with the stuff left out that's indeterministic. Here's the standard freeze or fry model in the 70s. And you all know this. The universe could recollapse into a fiery dungeon. That's the one going down. Or it could go flat or continue to accelerate, both of which are the freeze models where things become endlessly cooler and all life is forever gone. That was the cosmology that all of us who were doing theology and science in those days worked out of. If you use cosmology at all, most people didn't, but if they did, that was it. So my goal here is to show just real quickly some of the responses to that. The first one is a conflict model, eschatology as irreconcilable with cosmology. So Bertrand Russell, read that quote if you would, please, if you see yourself. That's a quote I used many, many times in courses and public lectures. Stephen Weinberg, I think, is the most clear, though. It is very hard to realize that this all is just a little tiny part of an overwhelmingly hostile universe, which faces a future extinction of endless cold or intolerable heat. And here it is. The more the universe seems comprehensible, the more it also seems pointless. Well, what a tragic view of nature. How could you do anything with that theologically? Well, one way you can do it, of course, is reductionistic, is reduce eschatology to cosmology. Don't talk about anything in eschatology that isn't in cosmology, which is not going to be doing theology, it's be doing science. And you get a good move here from Freeman Dyson, a wonderful paper that you can have endless intelligence and experience in an open universe. But Frank Tipler and John Barrow, an odd mixture, argued that even in a closed universe, you could have endless computation or interaction with these kind of computers at the end of time who would remember you. And that was resurrection, which is pretty materialistic view. I knew all those guys, but they were a lot of fun, as it were. Or you can keep them independent, right? The two basic models is let them conflict or keep them separate. So this is the irrelevancy of cosmology. And really, one of the best examples is process theology, because in process theology, eschatology is really subjective immortality. And Ian Barber and Marjorie Suhaki represents that point of view. Or there were some initial, attempts to do something with it. Read Moltmann's wonderful quote about the future. There can be no eternal life for human beings without the change in the cosmic conditions of life. So that's beginning to get at the kind of response that Lee is going to pick up and run circles with. Dennis Edwards, eschatology involves God's transforming the universe as a whole. So it's cosmology. It isn't just our local galaxy. And all that is within it, from clusters of galaxies to subatomic particles. So everything is transformed. I like that from Dennis, wonderful guy from Australia. Panneberg, really, as you know, developed the notion of prolepsis. The eschatological future is first instantiated in the bodily resurrection of Jesus. So this is a bold move where there is a future, a cosmic future, and that's where God works back into the present. But Panneberg never really wrestled with the challenge that the term future is not clear. I mean, the cosmic future certainly can't be the eschatological future in any simple sense. That's the problem. So what is the eschatological future if all we have is a cosmic future? I talked to Wolfhard about that quite a bit, but we never got too far. Ted has a wonderful idea of understanding prolepsis as, quote, temporal holism. The cosmos is created and redeemed from the future by the Trinitarian God. Excellent idea. Again, I like more clarity on what that future is. Is the one that scientists predict? No, it couldn't be. But if it's not that one, is it really a future, or is it really a hope? So just leave it there. John and I did a little more work. John advanced this wonderful notion of creation as ex vetera. The new is not a second creation. You don't wipe out the universe and recreate it. It is a resurrected world created ex vetera, out of the old. That, I think, is a really helpful theme. It means there's value the way the universe is now. And then in order to achieve that, there must be both continuity and discontinuity. And a number of us have worked in that idea. And then, of course, I've developed this idea of creative interaction. So you reconstruct eschatology in light of science. You look for new research directions in science out of eschatology. And hopefully those two meet. One last slide. Now we're in the current decades. This is when Hyung-Joo was doing his PhD work. And now gravity is partly integrated with the particle physics. That's absolutely astonishing, because that wasn't even talked about when I was in graduate work. And now it's being done so wonderfully. Hyung-Joo has published papers on this a lot. And it leads to, as he'll tell us tonight in much more detail, an infinity of new Big Bang cosmologies. And the key is, since you're integrating particle physics with general relativity, the indeterminacy in particle physics has an effect on the future of the universe, as it didn't in just the straight general relativity in cosmology when I was a kid. So let's exit from here, and thank you very much.
Okay, I'd like to say first that I'm really happy that all my doctor fathers are here. So Bob is here, Ted is here, and Philip is here. So I'm really, I feel really comfortable, because, I'm with my dear doctor fathers here for my talk through the CTNS public forum. So, so today I'd like to talk about a new hope for Christian eschatology in cosmic perspective, which is beyond the predictions of standard Big Bang cosmology. So let me begin. Right. So Big Bang cosmology is the standard theory that describes the history of our universe with a set of equations derived from the so-called Einstein field equations that describe the relation between space-time dynamics and mass energy distribution based on the theory of general relativity, proposed in 1915 by the famous physicist Albert Einstein. And the equation you see here, G mu nu is equal to 8 pi G T mu nu represents the 16 Einstein field equations. And here, G mu nu is the Einstein tensor that represents mass energy distribution in space-time. sorry. T mu is the stress energy momentum tensor that represents mass energy distribution in space-time. And G is the Newton's constant that determines the strength of gravity. And G mu is the Einstein tensor that represents geometry of space-time. Although the Einstein field equations look like a single equation, the tensor matrix you see from the slide, mu, indicates that they are composed of 16 different equations in total. In 1922, Alexander Friedmann proposed a set of differential equations, the so-called Friedmann equations, derived from these Einstein field equations by assuming that the matter in space-time geometry can be regarded as a perfect fluid and that the universe is spatially homogeneous and isotropic on large scales as equations that determine the physical evolution of our universe. So you see a couple of equations here. They are called the Friedmann equations. Here, A is the scale factor of the universe that measures the amount of expansion of the universe. And the rho is the energy density of the universe. And the P is the pressure of the universe. And lastly, K is the curvature, space-time curvature of the universe. So that represents the geometry of the universe. It should be noted that the assumption of homogeneity and isotropy, which is often referred to as the cosmological principle, reduced 16 different equations that could have been much more complex into a set of simple calculable equations that enabled cosmologists to calculate the physical evolution of a universe during its entire history under the assumption that its energy density, pressure, and the curvature at any specific moment of time are given. Okay, since it was recognized that the Friedmann equation built a universe that exploded from an initially extremely dense state with enormously hot temperatures, the so-called hot Big Bang state, and has continued to expand until now, there has been a debate for 4 decades whether our universe in which we live is indeed the Big Bang universe described by these Friedmann equations. The first evidence came in 1929 through the astronomical observations by Edwin Hubble. Hubble discovered that galaxies are moving away from the Earth with their recession velocities proportional to the distance from the Earth, which was consistent with the predictions of the Friedmann equations that the universe should expand, maintaining its homogeneity and isotropy. Putting the observed constant ratio of the recessional speed of galaxies to their distance measured by Hubble, the so-called Hubble constant, into the Friedmann equations, cosmologists were able to calculate the expansion of our universe in time quantitatively. Since then, the majority of cosmologists have assumed that Big Bang cosmology, as described by the Friedmann equations, correctly describe the physical evolution of our universe. Moreover, the accidental discovery of the cosmic microwave background radiation, which is called CMBR, in 1965 by Arno Penzias and Robert Wilson, confirmed that Big Bang cosmology describes even the very early history of our universe. The discovery of the CMBR played a crucial role in confirming Big Bang cosmology as the standard model in cosmology. As the existence of homogeneous and isotropic background radiation generated 380,000 years after the hot Big Bang state, filling out the universe was one of the unique predictions of Big Bang cosmology that was absent in any other competing theories. As it is confirmed that the history of our universe is described by a set of simple differential equations, since the early moment when the atoms, the basic components of life organisms, were first generated, the detection of the CMBR is evaluated as one of the most important scientific discoveries of the 20th century. But the reason is that the observed homogeneous and isotropic radiation was generated only 380,000 years after the hot Big Bang state, from which our universe has evolved for 13.8 billion years. In addition, along with the confirmations of other predictions of the theory, including the ratio of helium atoms to hydrogen atoms, specifically determined at the end of the first 3 minutes from the Big Bang, Big Bang cosmology has been validated even back to the moment extremely close to the beginning of our universe. Since then, the theory describing the history of our universe from the Big Bang with the Friedmann equations derived from the theory of general relativity with a critical assumption of homogeneity and isotropy has been called the standard Big Bang cosmology. Since this revolution in cosmology, physicists have begun to insist that the secret of our universe has been unveiled completely, as Big Bang cosmology seemed to allow us to look into the detailed history of our universe from the beginning to the present, and even to project forward to the end. But here there are challenges to Christian eschatology. The remarkable success of standard Big Bang cosmology does not necessarily mean that we have a bright future, as depicted in Christian eschatology. As a matter of fact, it is exactly the opposite. On the one hand, standard Big Bang cosmology unveiled the mystery of how the terrestrial environment in which living organisms, including human beings, could be formed out of a barren primordial universe in which there was nothing but elementary particles violently colliding with each other at enormously high temperatures. The expansion of our universe, as described by the Friedmann equations, explains how the temperature of the universe cooled down to allow the formation of atoms, molecules, stars, and galaxies, during which all life on Earth and the Earth itself were created. On the other hand, it predicts that neither we nor our environment will be able to persist in the far future. The reason is simple. When we rewind the tape with the Friedmann equation, by tape I mean the tape that contains the history of our universe, it is easily recognized that living organisms did not exist for most of the past 13.8 billion years. First of all, according to standard Big Bang cosmology, our universe did not even have atoms, the basic components of life organisms, in its early history. The Friedmann equations clearly suggest that our universe was too hot to allow the formation of any atoms, at least for the first 380,000 years. Moreover, the temperature of our universe was too high for more than 9 billion years for our sun to be formed, which means that the Earth, birthplace of life organisms, including us, had not existed for most of the history of our Big Bang universe. This implies that it is likely that the environment that could sustain life organisms had never existed for billions of years. If our universe did not have an environment that could sustain life organisms for most of its history, it is natural to expect from the dynamicity of our universe that such an environment might not persist forever in the future. More specifically, the Friedmann equations derived from the Einstein field equations predict that there are only 3 possible scenarios for the far future of the universe. As you can see from the diagram, closed, flat, and open, depending on the curvature of the universe, all of which should lead to what is apparently far from a life-sustaining environment, either freeze or fry. In the case of freeze, which is represented by the 2 graphs labeled open and flat, our universe will keep expanding forever, and thus it will keep cooling down to the temperature of absolute 0. In the case of fry, as represented by the graph labeled closed, it will stop expanding at some moment, and then in the future, collapse back into the initial hot Big Bang state with extremely high temperature. You can see that from the bottommost graph here. What does it mean? If it collapses back into the initial hot Big Bang state with extremely high temperature, then nothing but elementary particles colliding with each other with enormously energy will remain. Neither of them is far from a new heaven and new earth in which God's creatures, including ourselves, enjoy eternal life, or even a minimal material basis for such a new creation by God. It is clear that the predictions of standard Big Bang cosmology are in apparent conflict with Christian eschatology. Okay, while many Christian theologians view the evolutionary description of living beings, including human beings, as being in conflict with the traditional description of creation and responded to the challenge in various ways, only few Christian theologians discuss the challenge of the evolutionary description of the universe in detail in relation to Christian eschatology. For instance, Philip Hefner, who extensively discussed the influence of 20th century science on Christian doctrines, discussed this cosmology relatively little compared to other scientific theories, such as evolutionary biology. Although the challenges of Big Bang cosmology to Christian eschatology have not been considered a key issue by most Christian theologians, it should be acknowledged that there were Christian theologians who were aware of the apparent conflict between standard Big Bang cosmology and Christian eschatology and discussed it to a certain extent. Especially Christian theologians who gave the Gifford lectures, which are considered the most monumental lectures addressing the issue of relating theology and science in the late 1980s and the early 1990s, addressed the issue of how to relate the fate of our Big Bang universe predicted by standard Big Bang cosmology to the eschatological future in Christian eschatology. Nevertheless, despite their explicit discussions of Big Bang cosmology in relation to Christian eschatology, they tend to fail to propose a plausible idea of how to reconcile the hopeless predictions of standard Big Bang cosmology with what is expected from Christian eschatology, the eschatological hope. First, through his Gifford lectures in 1993, Arthur Peacock, you can see his picture here, extensively discusses how theology should respond to the challenge from the biological evolution of Homo sapiens with his background in biochemistry, and adds the discussion about the challenge from the physical evolution of the universe, emphasizing its role as what emerged as the environment for Homo sapiens. On the one hand, Peacock clearly recognizes and emphasizes the role of the universe for theology by proclaiming that the whole approach of his work is the working out of the notion of the universe itself as sacramental. He recognizes that the universe should become the environment for the new entity, the church, which emerged out of and beyond the biological evolution of Homo sapiens, and rightly points out that the relation of that new entity, quote, to the natural world has too often been overlooked. However, Peacock himself seems to overlook the challenge of the predictions of Big Bang cosmology when he claims that the eschatological hope cuts across, indeed transcends in the strict sense of the term, the now familiar predictions of the future on the physical timescale which scientists can provide, quoted from his book. Claiming that the Christian hope is quite otherwise than the predictions of Big Bang cosmology, Peacock explicitly separates the future of our universe predicted by Big Bang cosmology from the ultimate destiny of humanity that he considers to be in God, to be vouchsafed that beatific vision so nobly expressed in the last stanzas of Dante's Paradisio. At first, he seems to confront the challenge from the predictions of Big Bang cosmology when he introduces the arguments of Friedman Dyson and Frank Tipler, who suggested, on the basis of physics, intelligence might conceivably be able to survive the demise of the Earth and of the galaxy and universe, as an attempt to reconcile Big Bang cosmology and Christian eschatology. But there was a great attempt, of course. However, Peacock finally concludes that there can be no hope in such a physical cosmology suggested by Dyson and Tipler, because, quote, all the past evils and inhumanities that have been perpetuated in our known history will be forever present in the final state, quote, even if intelligence might be able to survive the demise of the universe. His conclusion that there is no hope in the future of our universe seems to exclude our Big Bang universe from the eschatological future in which God's creatures participate in the resurrection of Jesus. While he makes it clear that the Christian hope is in the nature of God as the self-offering, faithful, creating love revealed in the life, death, and resurrection exhortation of Jesus, it is a quoted sentence, Peacock only stresses that, quote, we can begin to participate in the life of Jesus here and now, without discussing how to participate in the death and resurrection of Jesus in the future. As a result, it becomes unclear how the sacramental role that our universe has been playing can be played in the eschatological future, so that it could become the environment for God's creatures to allow them to participate in the resurrection of Jesus. If the eschatological future is achieved only in the beatific vision that has nothing to do with the physical evolution of our universe, it becomes questionable that the new entity who participate in the resurrection exhortation of Jesus would actually emerge out of the biological evolution of Homo sapiens. Next, Ian Barber. Compared to Peacock, Ian Barber, who gave the People lectures in 1989 to 91, is more concerned about embodiment and goes further to confront the challenge of the predictions of Big Bang cosmology more seriously. Like Peacock, Barber also introduces the arguments of Dyson and Tipler and reaches the same conclusion that their arguments are inconsistent with the biblical message. However, his reasoning is distinguished from Peacock's. First, Barber points out that the Bible views the person as a unity of body, mind, and spirit, not as a purely rational intellect defined by information processing ability. In other words, unlike Peacock, Barber makes it clear that what participates in the eschatological future should be embodied, which implies that the environment itself, our universe, must remain as a physical entity, even until the eschatological future. It seems that this reasoning makes Barber confront the far future of our physical universe predicted by Big Bang cosmology more seriously than Peacock. It should be noted that Barber criticizes the concept of a technologically based salvation that seeks control of the cosmos, common in the arguments of both Dyson and Tipler. As Barber rightly points out, quote, though biblical eschatology takes many forms, all agree that future fulfillment will be the work of a personal God, as well as of humanity, not the work of humanity apart from God. I claim that for this divine involvement, Big Bang cosmology must have some characteristics from which God could open up the future, distinct from freeze or fry, which I will propose later. However, instead of taking the possibility of saving our universe with the work of God, Barber proposes possibilities that are problematic from the perspective of Christian eschatology based on the bodily resurrection of Jesus. What he proposes as new possibilities is that God can bring the eschatological future even in another creation. How does it sound? With this proposal, Barber further claims that the central value and meaning in process thought, which he chooses as a metaphysics for Christian eschatology, is essentially unaffected. Even if we think that life on Earth or in this universe will eventually be extinguished. It is a quoted sentence from Barber's book. Even if this proposal holds, one of the central claims in his reasoning for refusing Dyson and Tipler, that the embodiment should persist, I have two critiques of his proposal. First, it is contradictory to his other claim that, quote, our hope is based on the conviction that God is at work in the world and that we can cooperate in that work. Quote, if the eschatological future is brought on a different universe, having nothing to do with our universe, it cannot be viewed as an outcome of God being at work in the world where we can cooperate with God. The second critique, which is more important, is that the idea that God will annihilate our universe to create a new one is not acceptable in Christian eschatology based on the historical event of the life, death, and resurrection of Jesus. John Polkinghorne, who gave the Gifford lectures in 1993, makes it clear that, quote, the new is not a second creation ex nihilo, but it is the resurrected world created ex verita, affirming that, quote, involved in its coming to be must be both continuity and discontinuity. Just as the Lord's risen body bears the scars of the passion, but is also transmuted and glorified. Quote, Polkinghorne further claims that any realistic account of Christian eschatology should be based on the recognition that the new creation is not a second attempt by God at what he had first tried to do, the old creation, rightly pointing out that the new creation is the divine redemption of the old, suggesting the empty tomb and sharing of food as indications appearing within history of the transformed nature of eschatological matter. He claims that there should be some degree of intersection between the historical and the eschatological. With a theological conviction that God is in continual providential interaction within its history, he will bring about purposed ends, even if they are achieved along contingent paths. That's a quoted sentence. I interpret Polkinghorne's claim as that the universe in the eschatological future as a transformation of our Big Bang universe should inherit the character of the future state of our Big Bang universe, out of which creatio ex verita within the history of the universe described by classical general relativity, which seems to have a predetermined path to the heat death without any contingency. Theologically, it is required that there exists path boiling down to other than the heat death, to which Polkinghorne does not provide a concrete answer. Wilhelm Moltmann, who gave the default lectures in 1984 to 1985, a decade before Polkinghorne, also points out that the universe in the ultimate future should inherit the elements of continuity from the physical evolution of our universe, when he claims that the new creation presupposes the old one, distinguishing creatio ex verere from creatio ex nihilo. Similarly to Polkinghorne, he rightly points out that the idea of the resurrection of the body is lost completely if salvation is supposed to consist only of the blissful beatific vision of the disembodied soul, which I view as a strong critique of Peacock's eschatology. From this, he makes an important remark that once the hope that our universe will be redeemed is lost in eschatology, the Christian faith becomes a world-denying, world-despising Gnosticism, with a belief that without cosmology, eschatology must inevitably turn into a Gnostic myth of redemption, and there is no redemption for human beings, either without the redemption of nature. Moltmann suggests that there can be no eternal life for human beings without the change in the cosmic conditions of life, quoted from his book. However, claiming that the attempt to develop a scientific eschatology in order either to affirm or confute scientific ideas about the end of the world is pointless. Moltmann does not propose any idea in detail about how our universe might be able to achieve the cosmic conditions of life, clearly distinguished from the cosmic conditions for the far future predicted by standard Big Bang cosmology. While I agree with Moltmann that it is not appropriate to propose a concrete scientific model for cosmology as the only model for Christian eschatology, I claim that Christian theologians should be aware of the conflict between the models proposed by cosmologists and Christian eschatology, and offer directions for new scientific research programs by suggesting criteria from Christian eschatology. What is clear from the theological notion of creatio ex verere is that the universe ending with the heat death cannot be reconciled with any Christian eschatology, with hope, based on the resurrection of Jesus. I suggest that the predictions of standard Big Bang cosmology that the fate of our universe is predetermined to freeze or fry should be set aside in a search for other scientific cosmologies that might be more compatible with Christian eschatology. Another way to say this is that cosmologists should seek theories that allow future scenarios totally distinct from freeze or fry. It looks familiar to me. Unlike the early theologians who were hesitant to challenge the predictions of Big Bang cosmology, Robert Russell proposes that the predictions of standard Big Bang cosmology should be altered to reconcile with Christian eschatology using his method of creative mutual interaction, which he calls CMI. The central claim from CMI is that the interaction between science and theology is mutual, so that not only can science offer ideas for theological research programs, but also theology can offer ideas for scientific research programs. Russell's key claim in confronting the conflict between the eternal eschatological future and the temporal future of our Big Bang universe is that the challenge is mutual. First, standard Big Bang cosmology challenges Christian eschatology because if the predictions of standard Big Bang cosmology come to pass, there will not be a general resurrection, which takes away the hope of Christian eschatology that includes the universe. And second, Christian eschatology also challenges standard Big Bang cosmology, because if it is in fact true that Jesus rose bodily from the dead, then the general resurrection cannot be impossible. Russell further claimed that the challenge seemingly from science is not actually from science, but from a philosophical assumption brought to science, namely that scientific predictions such as freeze or fry must be true, because scientific laws are prescriptive, not just descriptive, and that the future will be necessarily what science predicts. Instead, Russell argues that if God chooses to act in a new way, the future will not be what science predicts, and thus the freeze or fry predictions for the cosmological future will not happen. Well, his main point is that this is not a contradiction of physics, but of the philosophical assumption due to Hume, that the laws of physics must be obeyed. They have ontological status. Since in Russell's view, the laws of physics are merely descriptive reflection of God's action as an ongoing creator. If God wants to create something new in the far future, that is not in contradiction with science, only with the Humean philosophical assumption about science. For his argument, it is theologically crucial to assume that the laws of physics are not prescriptive, but merely descriptive. Okay. Before analyzing Russell's proposal, it is worthwhile looking into two aspects of Pannenberg's theology, which provide the basis for Russell's proposal. First, Pannenberg's discussion of divine attributes derived from Hegel's notion that God embodies the world while transcending it plays a crucial role in Russell's proposal, as it makes the eschatological future inseparable from the temporal future of the universe. Russell adopts and develops Pannenberg's discussion of divine attributes with the aid of Cantor's mathematical notion of transfinite, according to which the infinite contains the finite, while transcending it. Based on this, Russell suggests that the temporal future finite time of the universe should maintain the elements of continuity as well as discontinuity to be inherited by the eschatological future, infinite eternity. His suggestion is in harmony with the concept of creative ex-veter, emphasized by Polkinghorne and Mortman, but in sharp contrast to the eschatology of Peacock and Barber, who tend to ignore the elements of continuity by regarding the eschatological future as symbolic expressions of trust in God that represent an ultimate framework for temporal history, not events in that history. This is a quoted sentence. Another important aspect of Pannenberg's theology that led to Russell's proposal is the concept of prolepsis, which denotes that God acts from eternity by reaching back into time to redeem the world based on the resurrection of Jesus. With a strong theological conviction of the eschatological future, Pannenberg suggests that God creates the world with the power of the future, not with the physical causality from the past, radically transforming the notion of divine interaction with the history of the universe, as well as with us. Clearly distinguished from Barber's eschatology based on the process thought, Pannenberg posits a perfectly redeemed universe in the eschatological future and starts from it to go back to the past retroactively. Similar to Moltmann, Pannenberg's conviction and hope originate from the historical event of the resurrection of Jesus. motivated by the concept of prolepsis, Ted Peters even claims that there must be a retroactive causality for God's creation distinct from the usual causality, according to which the past moment determines the present and the future, against what he calls the archonic fallacy. According to Peters' idea of retroactive causality, along with Pannenberg's idea of the power of the future, the eschatological future already exists as a source from which the past and the present of our universe originated. Okay, now my constructive proposal. Motivated by Russell's proposal, drawing on Pannenberg's theology, I further propose that Christian eschatology would offer scientific research programs in cosmology. The key for my proposal is to question and challenge the common assumption that led Russell and all other theologians introduced above to the conclusion that scientific predictions of Big Bang cosmology cannot be reconciled with Christian eschatology, namely that the fate of our universe is destined to freeze or fry according to Big Bang cosmology. The reason for this assumption is based on the deterministic nature of the classical theory of general relativity that underlies the standard Big Bang cosmology. According to classical physics, which includes the theory of general relativity, as well as Newton's classical mechanics, the motion of objects described by classical theories is predetermined once an initial condition is given, and thus is predictable with certainty, whether the object of description are material objects or even space-time itself. If the fate of our universe is determined by the mathematical equations derived from a deterministic classical theory, it is almost impossible to argue for God's providence as articulated by Pannenberg's notion of the power of the future, whatever the fate is. Unless there is some kind of unpredictability in the scientific theories describing the history of the universe, it is hard to imagine God transforming the universe in the future as the power of the future without disrupting the natural development of the future according to these deterministic laws. In this context, I suggest the accelerated expansion discovered unexpectedly in the late 1990s provides a clue to expect ontological unpredictability in describing the physical evolution of our universe. As described earlier, according to the original standard Big Bang cosmology, there are only 3 distinct scenarios for the far future of the universe, frequently referred to as closed, flat, and open. You may remember the diagrams I showed you earlier. Cosmologists in the 1970s and 1980s believed that the fate of our universe was already determined as one of those 3 scenarios, and that the uncertainty it had was only epistemological rather than ontological. Precise measurement of the distribution of galaxies would make them know without any uncertainty which of the 3 scenarios is for our Big Bang universe. Even though they did not reach consensus on which among the 3 distinct scenarios would be the fate of our universe, it was certain to them that our universe should decelerate due to the gravitational pull of matter in the universe, while there remain 3 distinct future scenarios due to the lack of data. However, astronomical observations in 1998, the supernova cosmology project led by Sol Perlmutter and the High Z supernova search team led by Brian Schmidt and Adam Rees, unexpectedly discovered that the expansion was accelerating instead of decelerating. This discovery led cosmologists to posit that our universe is filled with a strange form of energy that plays a role in accelerating the expansion. They called this hypothetical form of energy dark energy. To explain the existence of dark energy, cosmologists added the cosmological constant lambda to the original Einstein field equations, which Einstein had initially introduced in his equation, but soon abandoned. So G mu nu is equal to 8 pi G T mu nu becomes G mu nu plus lambda G mu nu is equal to 8 pi G T mu nu. This makes a crucial difference. This insertion transforms the Friedman equations into a new form that leads to the accelerated expansion of the universe. So you can see lambdas in the Friedman equations as well. A positive vacuum energy created by adding the cosmological constant lambda to the equations could be reinterpreted as an anti-gravity, providing a negative pressure that fills the universe and stretches the fabric of space, which is exactly the opposite of what ordinary matter does. Hence, it could drive an accelerated expansion of the universe as observed by acting against the gravitational pull that always tends to decelerate the expansion. The cosmological constant is so far the simplest explanation for dark matter. Thus, this new model with the added cosmological constant lambda, whose value was fine-tuned to match the observed rate of the acceleration of our universe, called the lambda CDM model, has been considered the new standard model for Big Bang cosmology since the 2000s. Despite its significant impact on cosmologists, which led to numerous papers proposing various models that incorporate dark energy as a relevant component of our universe and exploring its nature, theologians have hardly proposed a theological response to this new discovery, as far as I know. For instance, while Russell's cosmology book, published a decade after the discovery of the accelerated expansion, extensively discusses the theological implications of Big Bang cosmology, it views the accelerated expansion merely as a recent observation without altering its proposal that we should still abandon the philosophical assumption to reconcile with Christian eschatology. I assume that the absence of a thorough theological response to the accelerated expansion of our universe reflects that most theologians consider the discovery of the accelerated expansion to make no relevant difference from theological perspectives. Even if it might rule out the Fry scenario in the original Big Bang cosmology, as our universe should keep accelerating rather than collapse, it seems to maintain and even reinforce the other scenario, Reeves, which deprives the eschatological hope as much as does the Fry scenario. In contrast, I claim that the recent discovery of the accelerated expansion of our universe provides a clue of great theological importance that makes a crucial difference, especially for Christian eschatology, as it reveals ontological unpredictability for the future history of our universe, stemming from the quantum effect from quantum field dynamics that cannot be described by the classical theory of general relativity solely. I claim that this in turn could break the foundation of classical determinism in the theory of general relativity, as the accelerated expansion explained by the addition of quantum effect to the Einstein field equations reflects the possibility that some quantum effect might transform the fate of our universe into the one that is not predicted by the Einstein field equations in a current form. This reminds us of the often overlooked fact that quantum field dynamics could play a crucial role throughout the history of our universe, even to change its physical evolution into what is beyond the predictions. One might wonder why the quantum effects from the fluctuations of quantum fields were not reflected in the Einstein field equations initially. Okay, one might wonder why the quantum effects from the fluctuations of quantum fields were not reflected in the Einstein field equations initially. It is due to the classical nature of general relativity. Even though the standard model of particle physics is derived from quantum field theory, the quantum fluctuations of particles are truncated when their energy and momentum are substituted into the stress energy momentum tensor, C mu, in the Einstein field equations to calculate the expansion rate of our universe. Even though it is obvious that the source of the stress energy momentum tensor in the Einstein field equations is the standard model particles described by quantum field dynamics with quantum fluctuations, their truncation, due to the inability of the Einstein field equations to track the quantum fluctuations, has often been overlooked because the quantum fluctuations seemed not to affect the physical evolution of our universe. However, the unexpected astronomical observations of the accelerated expansion showed that quantum effects that have been ignored could dramatically change the physical evolution of the universe, reminding us that the physical evolution of our universe could sensitively depend on the dynamics of quantum fields. With this recognition, I suggest examining the possibilities of changing the deterministic prediction standard cosmology that might be opened up by the characteristics of quantum field dynamics in the framework of quantum field theory. Okay, there is another reason that cosmologists and theologians interested in the far future of our universe should focus specifically on the nature of dark energy. The observation of accelerated expansion implies dark energy is a dominant component of our universe, since our universe would decelerate if it were not a dominant component. As a matter of fact, according to recent observations, dark energy makes up almost 70% of our universe. According to analysis, it could be just a little more than 70%. Which is significantly larger than the amount of other matter. Moreover, the energy density of vacuum energy remains constant in contrast to the energy density of matter that decreases as the universe expands. This means that dark energy will become even more dominant than now in the far future. In principle, if the universe keeps expanding, the only relevant component of our universe will be dark energy in the far future. The historical fact that such a huge effect had been missed for decades since the standardization of Big Bang cosmology implies that cosmologists might still be missing some critical effects that could change the history of our universe dramatically. Moreover, it is most likely that the nature of dark energy holds a clue to those missing elements that might be able to change the prediction of standard Big Bang cosmology. However, this is not necessarily good news for Christian theologians hoping for the new creation in the eschatological future. As the more dominant the dark energy becomes, the faster the universe will approach the freeze. The question is whether there is any missing element that could open up the possibilities that the ultimate future of our universe could be distinct from the seemingly fast-coming freeze. Okay, as a response to this question, I suggest the following as a hypothesis. Okay, let me just read it. If the quantum effect from a simple quantum field dynamics change the past and the current evolutionary behavior of our universe, it would be natural to assume that more complex quantum field dynamics could change it more dramatically to the extent to change the predictions of standard Big Bang cosmology, even for the far future of our universe. With this hypothesis, I examined various models beyond the standard lambda CDM model that incorporate complex quantum field dynamics to find out models that would maximize the quantum effect on the physical evolution in the far future, even more than now. Among many other models, I proposed recent models based on the idea of quintessence as an example that opens up the possibilities that our universe might not end with the freeze ultimately. Okay, quintessence, the word meaning the fifth and highest element in ancient and medieval philosophy that permeates all nature, is an idea that the cosmological constant might not be constant, but varies both in space and time due to the complex quantum field dynamics. So that in the late 1980s and 1990s, cosmologists suggested that the cosmological constant could vary in space and time when a quantum scalar field with complex dynamics is introduced, and its energy density and pressure, varying both in space and time in a complex way, are added to the stress energy momentum tensor of the Einstein field equations. This idea was first proposed by Bharat Ratra and Philip Peebles and Christoph Latrich in 1988. Later in 1998, Robert Caldwell, Rahul Dev, and Paul Steinhardt expanded this idea to a more general type of time-varying dark energy, coining the term quintessence to refer to a hypothetical form of dark energy. This new form of dark energy, varying in space and time due to the dynamics of a quantum scalar field, began to be called quintessence among cosmologists. While it plays the same role as the cosmological constant, accelerating the expansion of the universe, quintessence is distinguished from the cosmological constant in that it has complex dynamics rather than constant. Okay, why I focused on the idea of quintessence is that this idea could lead to infinitely many distinct scenarios for the far future of our universe that include, but are not limited to, the freeze or fry, which I claim is of great theological importance for Christian eschatology. If quantum field theory determined the dynamics of dark energy, we would be able to predict the future of our universe at any moment precisely, regardless of how complex it is. However, because quantum field theory has infinitely many degrees of freedom, namely that any number of quantum fields with their own arbitrary dynamics could be introduced in principle, the dynamics of dark energy could also be arbitrary and unpredictable in principle. This means that theoretically, there are many possible scenarios for our universe to follow in the future, even maintaining the past and the present evolution the same to match observations. You have to find out from this diagram that all these three graphs share the common for the observations for the past and the present. That's the point. What should be emphasized here is that it cannot be predicted which of the infinitely many paths our universe is going to follow in the future, even if we could measure the past and present evolution with any precision. Therefore, it is not merely an epistemological unpredictability, but an ontological unpredictability based on the infinitely many degrees of freedom in quantum field theory. So even though you are seeing only 3 graphs here, actually we can draw infinitely many graphs here, all of which can maintain the past and the present evolution the same to match observations. Okay. It should be noted that this ontological unpredictability is unique to the quantum field theory, in which matter can be arbitrarily annihilated and created through complex quantum field dynamics. In contrast to simplicity of classical physics, in which the dynamics of particles is completely determined with no chance of their annihilation nor creation, complex dynamics of quantum field theory allows complete dynamics of quantum field to create new forms of mass energy, such as dark energy, in an arbitrary and unpredictable way. There is no way to predict the complete dynamics of quantum fields, as there could be infinitely many quantum fields, each having arbitrary dynamics in principle. Since those dynamics cannot be prescribed, all their effect on the stress energy momentum tensor in the Einstein field equations cannot be reflected in advance. For this reason, Big Bang cosmology initially calculated the expansion of our universe with another assumption, that the only components of our universe are the standard model particles, in addition to the assumption that our universe is homogeneous and isotropic. However, both assumptions did not be true in the framework of general quantum field theory. I propose various models of quintessence that posit new forms of mass energy with complex field dynamics, even distinguished from the constant vacuum energy, as an example that demonstrates the unpredictability of the future history of our universe. While one might still wonder if it is plausible to posit the existence of new forms of mass energy that have complex field dynamics beyond the ones described by the standard model of particle physics, it has already turned out from observations that our universe is filled with exotic matter other than the standard model particles. As I explained earlier, our universe is currently composed of 70% dark energy and 30% matter. As the physical evolution of our universe is sensitive to the ratio of dark energy and matter, it is critical to maintain this ratio at the current time. However, it turned out from observations that the ordinary matter described by the standard model makes up our universe less than 5%, which means that more than 3/4 of matter in our universe cannot be explained by the standard model. To explain this discrepancy, particle physicists have been proposing various models introducing a number of additional quantum fields by positing additional symmetries in nature, such as supersymmetry. Actually, that's one of the things I did through my PhD study in physics. To the original 17 fields in the standard model, to extend the standard model to various models beyond the standard model. What allows particle physicists to propose those various models is a characteristic of quantum field theory that any number of quantum fields with any dynamics could be introduced as long as they match the observation. It has long been implicitly assumed among cosmologists and particle physicists that there must exist exotic quantum field dynamics in addition to the one described by the standard model of particle physics to explain the existence of non-ordinary matter that is called the dark matter. The idea of quintessence, that our universe has an additional quantum scalar field with complex field dynamics varying in both space and time, is perfectly plausible in this context. It is true that there are many cosmologists who persist in the traditional cosmological constant with a belief in the cosmological principle that our universe should be homogeneous and isotropic, which is one of the key assumptions in the original Big Bang cosmology that turned Einstein's complex field equations into the simple Friedmann equations. If the field values for dark energy could vary both in time and space, the cosmological principle would not remain true anymore. However, the cosmological principle might be simply an assumption that is true only approximately. Moreover, recent cosmological observations suggest that the cosmological principle seems to be actually violated, questioning the validity of the lambda CDM model that has assumed that the cosmological constant should be constant over space and time. Especially, cosmological constraints obtained in 2024 from the dark energy spectroscopic instrument, which is called DEGI, measurement of baryonic acoustic oscillation, which made the largest 3D map of our universe and is considered the most precise measurement of the expansion rate of our universe, suggests that the quintessence is preferred over the cosmological constant. Okay, I suggest that when the idea of quintessence is combined with the infinite degrees of freedom in quantum field theory, it leads to the conclusion of great theological importance that our universe has ontological unpredictability. This means that the fate of our universe is no longer determined to be a single free scenario, but becomes unpredictable, even with observational data. Cosmologists already proposed various models based on the idea of quintessence that lead to distinct future scenarios, not only freeze, but also the other ones that have been considered ruled out by the discovery of the accelerated expansion. Even though it might look similar to the diagram of the initial prediction of standard Big Bang cosmology before the cosmological constant was added, the left diagram, it is totally different from the initial one, the left one, in that all the scenarios share the same history for the past and the present of our universe in the new diagram, the right one. I claim that this change turned the epistemological unpredictability in the standard Big Bang cosmology into the ontological unpredictability. Unlike in the case of standard Big Bang cosmology, in which precise measurements could discern one of the different scenarios, in the cosmology in which our universe could have additional components that evolve differently from the standard model particles, even varying in space and time, there remains ontological unpredictability. In sharp contrast to the initial assumption that precise astronomical observations will lead to a single scenario for the future of our universe that is freeze, various models proposed based on the idea of quintessence strongly suggest that there can be an indefinite number of models that are capable of fitting observed facts more or less adequately, as suggested by the traditional underdeterminational thesis. I claim that this, by making the future of our universe open through the ontological unpredictability, vitalizes both Pannenberg's idea of the power of the future and Peter's idea of retroactive causality, and also Moltmann's idea of adventus. The reason that the retroactive ontology made little sense to cosmologists was that it was clear from the Friedmann equations that the future of our universe should be determined by the past and the present. However, it is no longer true that the past and the present state of our universe determine its future due to a new possibility that our universe might have complex quantum field dynamics that have not been reflected in the Einstein field equations and cannot be fully reflected in principle due to its ontological unpredictability. The concepts used to describe the retroactive ontology, such as the power of the future, the adventus, and the retroactive causality, are no longer mythical concepts, but are plausible ones, supported by the ontological unpredictability obtained from the nature of quantum field dynamics. Okay, comparison between Russell's proposal and mine. My proposal has both similarities and differences with Russell's proposal. On the one hand, it is similar to Russell's proposal in that it reconciles with Christian eschatology by abandoning the central assumptions that have long been taken for granted by scientists. The standard model of particle physics has been considered the model that describes all the particles in our universe and their interactions completely. And the cosmological principle has been taken for granted. The universe must be homogeneous and isotropic. It is necessary to abandon these long-lasting assumptions to obtain the unpredictability, to vitalize the theological concept, to reconcile with Christian eschatology. On the other hand, these assumptions are distinguished from the philosophical assumption that Russell proposed as the one to be abandoned, in that they are not assumptions in philosophy, but assumptions in cosmology. In this sense, it is closer to the spirit of Russell's original CMI that Christian eschatology interacts with cosmology directly rather than with philosophy. Furthermore, whereas it is hard for scientists to abandon the philosophical assumption, many cosmologists are already doubting and abandoning those two assumptions in the original standard Big Bang cosmology based on scientific data. Okay, furthermore, I suggest that the infinite degrees of freedom of quantum field theory provides an explanation that could replace Cantor's notion of transfinite that Russell used as a model to describe the relation between God's eternity and the temporality of creatures. While it is obvious that only the final quantum fields are going to be actualized, even until the far future of our universe, regardless of the scenario that our universe will follow, it maintains the potential possibility that any of the infinite degrees of freedom could be actualized at any time. For our universe to maintain ontological unpredictability, it should reflect the character of infinity, but is distinguished from absolute infinity as it remains finite until the end. This resonates with the keen character of transfinite that Russell uses to explain the relation between the eschatological future and the temporal future of the universe, based on Tannenberg's discussion of divine attributes. The strength of using the characteristics of quantum field theory is, first, it describes physical world, our universe, directly, unlike Cantor's mathematics, which describes the mathematical world. And second, it provides a way for Christian eschatology to be reconciled with physical cosmology. Okay, this will be my last slide and last comment before closing my talk. Lastly, I'd like to remind the audience that among the possibilities for the far future of our universe, there exist some that could make Christian eschatology more plausible. In contrast to the assumption that our universe will end in a heat death, it is not implausible to suggest that our universe could be in a state that could sustain the complex forms of matter in the far future. It might be irrelevant scientifically, but it is relevant theologically because creatio ex verere in Christian eschatology requires that our universe should maintain some element of continuity in the far future of our universe to be carried into the new heaven and the new earth. The infinite number of degrees of freedom in quantum field theory could be used as a source that could guarantee the possibilities that our universe could overcome the heat death. While the characteristic of quantum field dynamics suggests this as a possibility, quantum field theory itself would not actualize those possibilities. It requires an act of actualization beyond the theory of physics. Theologically, this could be interpreted as requiring God to open up the possibilities that would lead our universe to the resurrection. Among others, that would lead it to permanent death. Without the power of the future, adventus, or retroactive causality, we cannot hope for the resurrection of our universe. Nevertheless, the theological conviction that our universe, along with us, will participate in the resurrection of Jesus makes us hope and expect that God will redeem our universe out of the death predicted by the standard Big Bang cosmology. Thank you for listening.
Thank you very much, Hyung-Joo.
Thank you.
That was very detailed and very fascinating. I do want to call attention to a link I'm going to put in the chat now, that this is a blog post that Ted had published upon the successful dissertation defense from Hyung-Joo, which also talks about this project in general. So feel free to read that as well if you're interested. And we do have some time for questions. So if you would like to use the raise hand button under the reaction, or if you want to maybe type in chat your question or say, I have a question, I can call on people. So it looks like Mark has his hand up first.
Wonderful speech. Thank you very much, Hyung-Joo. I'm wondering, is it the isotropic assumption that makes it so that they assume that only classic geometries, the flat plane, the anti-curved plane, and the curved plane are the only real options? I mean, why not fractal geometries? Why not folding in complicated geometries and all the rest? Thank you.
Right. Yeah, actually, okay, actually, to answer the question, it can become very complicated. However, there are different types of geometry, and Einstein field equations assumes that the geometry of our universe is very simple. So that means we don't have any fractal type geometry, but we have three simple geometry for the universe, assuming that he derived the field equations and from that the Friedmann equations are derived. In that sense, we have only three simple geometries, Euclidean geometry, and also about your question about the isotropy. All those three scenarios, I mean, regardless of the curvature, the Friedmann equations assume in common that the universe is homogeneous and isotropy. So all those scenarios assume the isotropy condition.
Well, I think I will jump in with a question that is probably unfair. So you can just tell me to forget it, because it is actually something that I haven't read the article myself because it was just published on Monday. But my understanding is that researchers have calculated that white dwarfs and stellar black holes decay at the same rate, which they were not expecting. So I'm curious that would that serve as another example of unpredictability that we might find in cosmology that could further support your argument?
That's a great question, and so I didn't read that paper, but that is I'm really happy to hear that question, because that's what I want from theologians. So theologians now, with this lens, whenever cosmologists announce something like that, we can interpret that way. We can ask this kind of question, right? So that's that was my aim. That was the aim of my talk. So I'm very glad to hear your question, and I think I have to admit that I didn't read that paper. However, that makes sense to me, that if my understanding is correct and your understanding is correct, then it could be one clue that our universe might have had different earlier, a different history in the early times, in the early history. So yeah, so if that supports of standard Big Bang cosmology is not correct, then we can more strongly argue that, oh, the unpredictability worked there. So there will be the response. And as I said, the most clear example that plays that role is the DEGI experiment I introduced during my talk. So DEGI experiment clearly showed that dark energy should have had different values in early times, early history of the universe. So your question, the topic you're suggesting could be similar to that as well. But that's my kind of rough guess because I didn't read the paper.
Thank you. Yeah, Phil.
That was a fantastic presentation. It was at the level of your doctoral defense, which is also very sophisticated, as the four of us sat in a room or a Zoom room. But you've added elements that weren't a part of that initial presentation, and I'm very pleased. I did have one specific question, however. On about 4 or 5 slides back, you said in a slide, quote, "While it is obvious that only the finite quantum fields are actualized even until the far future," and then the second part of the clause is what you defended. "Our universe maintains the potential possibility that any of the infinite degrees of freedom could be actualized at any time." What I dispute is the beginning of the claim, or rather, let's understand it as a question. Why is it obvious that only the finite quantum fields are actualized even into the far future? So that I don't understand.
Okay, so actually, that is related to Cantor's notion of transfinite. That I introduced during my talk. Bob used as an example to illustrate the similarity and difference between the infinite and finite and eternity and the temporality. So actually that is a very great question, Philip. And I would say, for example, particle physicists has long assumed, as I said, there are only 17 fields actualized in our universe. Okay, that means, and that has been a good enough model to describe all the particle dynamics in our universe. So cosmologists or particle physicists would laugh if someone says, "Oh, there are actually infinitely many quantum field dynamics that plays a crucial role." So that doesn't make sense at all, because we have been using only 17 quantum fields to describe the entire history of our universe for a while. However, what I'm suggesting is that dark energy and the model of quintessence suggests is that, oh, it seems that there are more quantum fields that are involved in the physical evolution of the universe. That's what the cosmologists recently found. And then the next question we can have is that, oh, if we can add 1 or 2 more quantum fields, what about 3? What about 4? And from the nature of quantum field theory, I found out, and I'm pretty sure that particle physicists will agree, that quantum field theory itself, in principle, has infinitely many degrees of freedom for the quantum field.
So Hyung-Joo, let me just jump in. I have to leave in a moment for another meeting, but I dispute the word obvious. It's not obvious to me that only finite quantum fields are actualized. It's obvious that so far, but it's not obvious that only they are actualized, quote, even until the far future. We don't know that. And I think your argument depends on the possibility that before the far future, other types of quantum fields could be actualized, which I agree with you. The physics says yes.
Yeah, and let me give you a brief response. Actually, I have in my mind that in the eschatological future, all the infinite degrees of freedom could be actualized. That's what I have in my mind. But until now, particle physicists are sure that only a certain number of quantum fields are actualized in our
Yes,
universe.
we agree. But why do you say obvious that even into the into the long-term future, it's not, it's obvious that it won't happen? I think your
Okay,
argument
so
is it
Mhm.
can well happen. It is not physically strange to imagine this happening.
You're right in terms of the ontological unpredictability that I argued throughout my talk. Yeah.
Perfect. Thank you so much.
I think someone
Yes,
is raising
Jim,
his
go
hand.
ahead.
Okay. I'm not sure I'm going to state this correctly, but one of the things that I am thinking theologically is that it seems to be very easy for us to jump to resurrection
Mhm.
and forget death.
Mhm.
And yet the central emphasis of, for example, Paul in Corinthians, I will know nothing amongst you except the crucifixion.
Mhm.
It seems to me that at least analogously, theologically, with science, that the standard cosmological reality is synonymous or at least analogous to death.
Yes, I agree.
And I know that this has been talked about, and entropy and all of this stuff has that thing. Now, what I see in our theology is that Jesus actually embraces death.
Mhm.
So I'm just wondering that it seems that your paper, and I understand why, jumps to a scientific possibility with the quantum field, etc. I'm just wondering what the death would be like, because if there's discontinuity,
Mhm.
what is it that would bring about a death of that which is discontinuous and into something new? And I understand the idea of the unknowns of breaking symmetries and things like this, but it seems to me there has to be something analogous to the resurrection which was not caused by nature.
Mhm. Okay.
In other words, nature built into nature did not cause the resurrection.
Mhm.
It was not a quantum jump, as far as I know.
Mhm.
It was an act of God, but within human history. And that is the creation of the new creation.
Mhm.
And well, I think you get my point.
Yes.
I'm trying to figure out, why do we not allow death to be death?
Right. Thanks for your great comment and question. And I would answer this way. So I didn't say that um, the physical evolution of our universe will necessarily jump into the resurrection. It can go into the death as well. For example, according to the predictions of standard Big Bang cosmology, as I already introduced, we have three scenarios which lead to definitely to the death, right? So what I suggested was that, there is a way that the ultimate future of our universe is distinct from the heat death scenario. That was my claim. However, we can say even our universe can experience the heat death, for example, before that resurrection. So what quantum field dynamics suggests is that, so for example, we can imagine this scenario. The universe could go into the heat death, and then the characteristic of quantum field dynamics could give a possibility that our universe in the heat death, escape or overcome the death it already experienced. That could be one scenario that we can imagine. However, because of the ontological unpredictability, we cannot say for sure that, oh, our universe will experience the heat death and then will escape from that heat death. We cannot say that. However, what I suggest is that the characteristic of quantum field theory opens up that possibility as well. We don't know, specifically which scenarios will be the actual scenario that would occur in the history of our universe. But what I'm suggesting is that, ending in the heat death is not the only scenario predicted by cosmology. That was my whole point.
Thank you. Thank you.
Did that help?
Yes.
And I appreciate your question. It actually I don't have enough time to discuss that, but it is of very great theological importance, I think. So thanks for your comment. Yeah.
Great. Any final comments, either from Bob or from Hyung-Joo, to wrap us up?
Congratulations, Hyung-Joo. That was brilliant and wonderful.
Thank you, Bob. I think I spent too much time.
Okay, well, please join me once again in thanking the Reverend Dr. Hyung-Joo Lee for his presentation. And thank you for being with us this evening.
Thanks for having me.